In this machine learning class, we will see the second part of feature extraction, that is principal component analysis. This is one of the important methodology for reducing the dimension of data set. Okay, so in this class, we will see what is principal component analysis, objectives of PCA, steps for PCA, that totally 8 steps are there, then one solved problem. After that, we will see the applications of PCA. Okay, so by using PCA, we can reduce the dimension of data set. For example, so this is the two-dimensional data set. By using PCA, how this two-dimensional data set will be reduced into one-dimensional data set. So this is the thing we will see in today's class. Principal component analysis. Every data set has multiple attributes or dimensions. Okay, attributes. The field of data set. The field of data set are called as attribute. Okay, many of which have similarity with each other. Okay, similarity. Okay, for example, the student database, weight of the person are related to height of the same person. Okay, if height is increased, then weight also be increased. If weight is increased, then height also be increased. Okay, here the weight and height are sum of similar to each other, right? If age is increased, then height also be increased. If age is increased, then weight also be increased. Okay, those are directly proportional to each other, right? So from these three, we have to take any two is more than sufficient, right? With respect to our problem, we can select the required feature, right? That is, if the features are less in number, as well as similarity between each other is very less. Similarity between each other is very less. This is important. Then the machine learning will perform better. So otherwise what will happen? The time complexity and space complexity will also be increased. So to decrease the complexity, we have to take only the less number of features for our computation. For that purpose, we can use the algorithm principal component analysis. So in PCA, the new set of features are extracted from the original features, which are quite dissimilar in nature. So no feature is similar to other feature. That is, an n-dimensional feature space, okay, which is already existing, gets the transformed to m-dimensional feature. Here, m less than n. Okay, m number of features will be reduced to m number of features. Okay, and another thing, the dimensions are orthogonal to each other. Orthogonal means completely independent of each other. Okay, there is no dependency as well as there is no similarity. Similarity between the features, right? In PCA, let us try to understand these basis vectors. We know that vector is a quantity having both magnitude and direction. Okay, magnitude and direction, and the vector can also determine the position of a point relevant to another point in Euclidean space. Okay, so in the Euclidean space, the position of point will be determined by the vector. Okay, that is 2 or 3 or n-dimensional space. Okay, here this is two-dimensional space. This is x and this is y, two-dimensional space. And the vector space is set of vectors. And the vector space have a property that they can be represented as a linear combination of smaller set of vectors. The linear combination of smaller set of vectors are actually called as the basis vector. Which is basis vector? The linear combination of smaller set of vectors. Hence, the vector V in vector space can be represented as V equal to summation of I equal to 1 to n ai ui. Here, A is the n scalars, A is the n scalars and U represent the basis vector. Okay, and all the basis vectors are orthogonal to each other. That is, all are independent. There is no dependency between the basis vectors. Here, the orthogonality of vectors in n-dimensional vector space can be thought of an extension of vectors which being perpendicular in two-dimensional vector space. See, for example, this is vector 1 and this is vector 2. So, vector 1 and vector 2 are exactly perpendicular to each other. That is, the two orthogonal vectors are completely unrelated and independent to each other. Right? Here, each vector in orthogonal set can be expressed as linear combination of basis vector. Right? So, this helps in decomposing the vectors. Okay? Decomposing the vectors to number of independent components. Okay, so how many independent components are there in data set? Okay, by using this PCA, we can easily identify the independent component in the data set. We can select only those independent components so that the complexity of the machine learning problem will be very much reduced. So here, the feature vectors will be transformed into vector space and these vector space will be transformed into principal component. Okay, now we just try to understand that the principal components are orthogonal to each other because the vector from vector space only transformed into the principal component, isn't it? Hence, the principal component must be orthogonal to each other. That is, they are completely independent to each other. There is no relationship between the principal components. Right? Here, the set of future vectors which may have similarity with each other is transformed to set of principal components. The principal components are completely unrelated or the principal components are independent to each other. Okay, here the principal component captures the variability of orthogonal feature space. So what are the variability there? By using principal component, we can easily capture those things and the number of principal components derived is much smaller than the original feature set. For example, the original feature set is n number of features there in a data set and now we are going to construct only m number of features. Here m is very much less than n. Very much less than n. Okay, so m is the principal component. And next, let us see the objective of PCA. There are three important objectives. The first one is new features are distinct. That is, covariance between new features or the principal component is 0. That means the new feature is otherwise called as principal component. Okay, so the covariance between principal component is 0. Right? The second one is the principal components are generated in order of variability in the data. Okay, based on the variability of data, the principal components are created. Right? That means the first principal component should be captured the maximum variability and the second principal component should be captured next highest variability and etc. So based on this way, the new principal component will be created. Okay, and the third objective is the sum of variance of new feature. New feature is nothing but the principal component, isn't it? So the sum of components of principal component should be equal to the sum of variance of original features. Okay, so this is another important point of the PCA. And now let us see some of the common terms which are used in PCA. The first one is dimensionality. Dimensionality means a number of features or variable present. Number of features or variables in the given data set. Okay, which is called as dimensionality, we have already seen. Okay, that is the number of columns present in the data set is called as dimensionality. And second one is correlation. Correlation means how strongly two variables are related to each other. So this is called as correlation. Okay, that means if anyone changes, the other variable should also get changed. Okay, if two variables are related to each other, if this one get changed, then that will also affect the second variable. This value will also be changed. Okay, so this is called as correlation, and the correlation values range from -1 to +1. Okay, so -1 means if the variables are inversely proportional to each other. That means if this value increased, this value will get decreased. Okay, so this is inversely proportional to each other. And +1 means if the variables are directly proportional to each other. Directly proportional means if the first value will get increased, then the second also get increased. Okay, so this is directly proportional. And the third important term is orthogonal. Orthogonal means it defines the variables are not correlated to each other. Okay, that means those are independent to each other. That means the relation between the pair is 0. Okay, 0 means the values are not related to each other. So this is orthogonal. And the fourth one is eigenvector. Eigenvector means if there is a square matrix M, a non-zero vector V is given, then V will be eigenvector if AV is scalar multiple of V. V means vector. Okay, so this is eigenvector. And the fifth one is covariance matrix. That means a matrix containing the covariance between a pair of variable is called as covariance matrix. And next let us see the steps for PCA. There are 8 steps. The first one is getting data set. So getting data set means getting input data set, and that will be divided into 2 parts. First one is training set X and validation set Y. Okay, 2 set of input data is there, and second one is representing the data into a structure. Okay, now the data will be represented into table structure. We try to construct the table structure. Okay, here two-dimensional matrix of independent variable X. Okay, independent variable X means the field of the data set. That should be, the field should be independent. Okay, that is each row corresponds to the data item and the column corresponding to features. Okay, the row is data item or records, and the column corresponding to features. See, this is the column. This is the column, isn't it? So the column corresponds to features. Features means attributes, right? And the number of column is the dimension of the data set. How many columns are there? That is represented as the dimension of data set. The third step is standardizing data. Standardizing data means from the matrix X, that is the input matrix, take any of the feature which is having high variance, okay, and also more important, and that should be compared with low variance feature. Okay, here the importance of feature is independent to each other. That is, these two features are independent of the variance feature. Then divide the data items in a column with the standard deviation of the column. Okay, so we need to divide the data set, and the new matrix is called as Z matrix. Okay, and the fourth step is calculating the covariance of Z, that is the new matrix. Okay, here we need to find the transpose of X and multiply the transpose matrix with Z matrix. Okay, Z transpose into Z is the covariance of matrix Z. So this is covariance. In the fifth step, we have to calculate the eigenvalues and eigenvectors for the covariance matrix Z. Okay, when come to eigenvector, it is the direction of axis with the high information. So this is eigenvectors. Okay, and the coefficient of these eigenvectors are defined as eigenvalues. Right, and the sixth step is sorting the eigenvectors. So we need to sort the eigenvectors in descending order. Accordingly, the eigenvectors of matrix P of eigenvalues should also be sorted. So that should also be sorted in descending order. Then the resultant matrix will be P star. In step 7, we need to calculate the new features or principal component. Okay. Now multiply the P star, that is what we define now, with the Z matrix. P star with the Z matrix, and the resultant matrix is called as Z star matrix. Okay. Here each column in Z star matrix is independent to each other, and this is called as principal component. Okay, the columns of Z star are called as principal component. And remove the less or unimportant feature from the Z star, and we need to keep only important features here. Let us see one example for this PCA. Here we are having two features, that is two columns in the table. First one is X and second one is Y. And we are having four records. The first record, second record, third record, fourth record. So we are having four records. Okay, the data set is actually like this. And this is the X value. Okay, this is X and this is Y. Okay, here we are having four records. First, second, third and fourth record. First, let us see the step 1. Derive from the given data set, we need to identify the number of features is 2 and number of samples are 4. Okay, small n represent the feature and capital N represent the samples. And now let us try to compute the mean of variables. So we are having two variables X and Y, isn't it? So X bar, which is equal to 8, and Y bar, which is equal to 8.5. Okay. The third step, we try to compute the covariance matrix. Here we are having two variables X comma Y. So two variables are there. So the number of ordered pair are 2 power 2, which is equal to 4. Okay, so XX, XY, YX and YY. So these four are ordered pairs of X comma Y. Here first we need to find the covariance of all ordered pairs. So the formula for finding the covariance of Xi comma Xj, for example, this is X and this is Y, which is equal to 1 by n minus 1. N minus 1, capital N means number of variables. So number of samples. How many samples we are having? 4 samples. So capital N is nothing but 4. Capital N is nothing but 4. Small n equal to 2, because we are having 2 number of variables. Okay. That is covariance of Xi comma Xj, which is equal to 1 by n minus 1 summation of k equal to 1 to n xik minus x bar into xjk minus x bar. Okay. So now we need to find the covariance of x comma x. Covariance of x comma x, this one. Okay, which is equal to 1 by n minus 1 summation of k equal to 1 to n xk minus x bar whole square, because both the covariance of same x only, isn't it? So the value is 14. Okay, that is 1 minus 1 by 4 minus 1. 1 by 4 minus 1 into 4 minus 8. 8 is nothing but x bar. X bar value is 8. Just now we have seen, isn't it? So 4 minus 8 whole square. See, 4 minus 8 whole square, 8 minus 8 whole square, 13 minus 8 whole square, and 7 minus 8 whole square. Here the value is 14. And next we need to find the covariance of x comma y. Okay, here 1 by 4 minus 1, this 4 is nothing but number of records, isn't it? Into, see, 4 minus 8, 8 is x bar, 11 minus 8.5, 11 minus 8.5. So 8.5 is equal to y bar. We have seen, isn't it? So x bar value is 8 and y bar value is 8.5. Okay, plus, see this one, 8 minus 8 into 4 minus 8.5, 4 minus 8.5, and the third one, 13 minus 8 into 5 minus 8.5, and the last one, 7 minus 8 into 14 minus 8.5. So the value is minus 11. So just like the same, the covariance of y comma x is also minus 11, and the covariance of y, that value is 23, right? And now we need to find the covariance matrix, that is n into n, that here we are having 2 by 2. Okay, so S equal to covariance of x comma x, x comma y, y comma x, and y comma y. The values are 14, minus 11, and 23. And the fourth step, we need to find the eigenvalue, eigenvector, and normalized eigenvector. First, let us find the eigenvalue. Okay, eigenvalue is determinant of S minus lambda I, which is equal to 0. And I is identity matrix, we know that, and the lambda is eigenvalue. What is S? S is nothing but covariance matrix. So just now we have to compute, we computed the covariance matrix. Okay, now uh, uh, the deterministic value is minus 14 lambda, minus 11, here minus 11, this is 23 minus lambda, which is equal to 0. Okay, and finally we need to compute two eigenvalues. This is lambda 1 and this is lambda 2. So we can see the lambda 1 is higher than this lambda 2, hence we can compute, or we can declare that lambda 1 is the principal component. Now we need to find the eigenvector of lambda 1. Okay, so to find the eigenvector, S minus lambda 1 into I multiplied by u1, which is equal to 0. Here S, we know that this is a covariance matrix and lambda 1 is largest principal component, and I is identity matrix and u is eigenvector. Now we need to multiply the eigenvector with our matrix. Okay, once we multiply these two, then we will get this particular matrix, which is equal to 0. From this matrix we will get two linear equations. First one is, see this one, this equation, and second one is this particular equation. Okay, see from this equation, u1 divided by 11, u1 divided by 11, which is equal to u2 divided by 14 minus lambda 1, which is equal to t, which is equal to t. Okay, if the t value is equal to 1, then u1 is 11 and u2 equal to 14 minus lambda 1, isn't it? So the eigenvector of u1 of lambda 1, which is equal to 11, 14 minus lambda 1, which is equal to 11, 14 minus The lambda 1 value we know that 30.3849. So which is equal to 11 minus 16.3849. Now we need to normalize the eigenvector u1. Okay, which value is e1, right? So e1 which is equal to, see, 11 divided by root of 11 square minus 16.38 whole square. See these two values. Simultaneously, minus 16.38 divided by root of 11 square minus 16.38 whole square. Okay, these two values. Now we will get the E1 value. E1 value, we are having two values. Okay, these two. So simultaneously we have to follow all the steps to find the eigenvector for lambda 2 also. Now this is the E2 value. Okay. And now we have to derive a new data set, that is reduced to one-dimensional data set with the first principal component. Okay, so this is our original data set. From the original data set, we need to derive a new data set with PCA, only principal components. Okay, so P11. So this is the P11, 12, 13 and 14. P11 equal to E1 transpose multiplied by 4 minus 8, 11 minus 8.5. 4 minus 8 means x bar. 11 minus 8.5 means y bar. Okay. So, what is E1? E1 is 0.5574 and minus 0.8303, isn't it? Now, E transpose is this one. E transpose into minus 4, 2.5. So these values, which is equal to minus 4.3052. So this one. Okay. So simultaneously we need to compute P12. The value is 3.7361. P13. The value is, see here, 5.6928, and P14 is this one. So what we did so far? So this two-dimensional table now converted into one-dimensional table. Here two dimension means two features x and y are there. Here we are having only one feature PC. Right? 2D is converted into 1D now. Okay. Now the step 6, which is another important step here, the coordinate system for principal component. Okay. For that, first select the mean of x comma y. So let us take this as x-axis and this is y-axis. This is y-axis. Okay, what is the mean value? 8, 8.5. X value is 8, this one, and y value is 8.5. Okay, so that will come in this point, x bar minus y bar. Okay, now this is our new origin. Okay, this is new origin. So previously this was our origin 0, 0, isn't it? But after this, this will become our new origin. Hence, this is our y-axis and this is our x-axis. Okay. From here, we need to find the E1 value and E2 value. So E1 value is 0.5 minus 0.8. Okay. From here, 0.5 is this one and 0.8 is this one. That may come approximately in this place. Okay. And E2 value 0.8 plus 0.8. That may come here. Okay. Approximately in this place. Okay. So this is E1 and this is E2. Now let us change the color so that it will be easy for understanding. So from we need to draw the line for E1 and E2. From the origin we need to connect these two things. Okay. From here we need to draw the line. So this is E1 and from here we have to draw the line and this is E2. Okay, now E1 and E2 are perpendicular to each other. Okay, so this is negative side of E1 and this is negative side of E2. Negative side of E2. Okay, after that place the table values on E1. Which table value? This particular PC1 table value. Okay, just change the color. So for initially minus 4.3052. For example, minus 4 from here to 4 minus 4.3052 maybe here in this place. Okay, in this place and 3.73. So from here to this is 3.73. Okay, after that 5.69. So from here 5.69 may come in this place. After that minus 5.12. Minus 5.12 may come in this place, for example. Okay, from here only we have to compute. Okay, so all the table values are placed on E1 axis. E1 axis. Now all the values lies on only the E1 axis. Okay, that is single dimension. That means the maintenance of single dimension is very easy when compared to two dimensions. Hence, the time complexity and space complexity of those algorithms will get very much reduced. And now let us see the applications of PCA, right? The most important feature of that is application of PCA is dimensionality reduction technique. That is what we have seen up to this. After this, it is also used in computer vision and computer image compression and etc. Okay, these are important applications of PCA, and it also used to find the hidden patterns if the data set has high dimensions. That is, in the high dimensional data set, we can use PCA to identify the hidden patterns, and some fields where PCA used are finance, data mining, psychology and etc. So far we have seen the principal component analysis, which is otherwise called as PCA, from feature extraction, and in this class we have seen what is PCA, objectives of PCA, steps for PCA, solved problem. Okay, after that we have seen the applications of PCA also. Applications of PCA also. So in the next class we will see the singular value decomposition and linear discriminant analysis. That is the part 3 of feature extraction from second unit, right?